Tonight we're going to confront something that sounds impossible, but is absolutely true. There are regions of the universe that we will never see, not because our telescopes aren't powerful enough, not because we haven't figured out the right technology yet, but because the universe itself has made it physically, fundamentally, permanently impossible. Light from those regions is racing toward us right now, has been racing toward us for billions of years, and it will never arrive. The space between us and those distant places is stretching faster than light can cross it. There's a wall around everything we can observe, and that wall is closing in. What lies beyond it is lost to us forever, and by the end of tonight, you're going to understand exactly why, and why it means the universe we see is almost certainly not the whole story. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing on your end, but it makes a huge difference for me. Now, let's begin. Let's start with something you do every single day without thinking about it. You open your eyes and you see the world around you. The walls of your room, the furniture, the people standing near you. Everything appears instantly. You open your eyes and the world is just there. No delay, no lag, no buffering, no waiting. It feels instantaneous, as if seeing is something that happens in zero time. You flip a light switch and the room is illuminated. You glance at a friend across the table and you see their face. It all seems to happen in the same moment. Immediate, effortless. But here's the thing, it's not instantaneous. What you're actually doing every time you open your eyes is collecting light. Photons, tiny packets of electromagnetic energy, are bouncing off objects around you and entering your eyes. Your retinas absorb those photons, convert them into electrical signals, and your brain interprets those signals to construct an image of the world. This process feels instant because the distances involved are so small. The light bouncing off your wall and hitting your eye travels maybe 3 or 4 meters. At the speed light travels, that distance is covered in roughly 10 billionths of a second. That's so fast that no human being could ever perceive the delay. No instrument we use in daily life could detect it. As far as your brain is concerned, you're seeing things as they are right now in this present moment, in real time, but you're not. You're seeing things as they were 10 billionths of a second ago. The light took time to reach you. It's an unimaginably small amount of time, true, but it's not zero. And this tiny, seemingly insignificant fact, the fact that light takes time to travel from one place to another, has consequences so profound that they reshape our entire understanding of the universe. Because when the distances get bigger, the delays get bigger too. And when the distances get truly enormous, on the scale of planets and stars and galaxies, those delays don't just become noticeable. They become barriers, walls, permanent, impassable boundaries that define what we can and cannot ever know about the cosmos we live in. Everything we're going to talk about tonight, every limit on what humanity can observe, every horizon that separates the known from the forever unknowable, it all comes back to this one deceptively simple idea. Light is fast. But light is not infinitely fast, and the universe is very, very large. Light travels at about 300,000 kilometers per second. To be precise, it's 299,792.458 kilometers per second. But for our purposes tonight, 300,000 is close enough. That's roughly 186,000 miles per second. It's the fastest speed anything in the universe can achieve, And this isn't just a practical limit, some engineering barrier that we haven't figured out how to break yet with better rockets or more powerful engines. It's a fundamental law of physics, woven into the very fabric of space-time itself. Albert Einstein showed us this more than a century ago with his theory of special relativity, published in 1905, and every experiment we've conducted since has confirmed it without exception. Nothing with mass can reach the speed of light. Nothing can exceed it. Not in theory, not with better technology, not with unlimited energy, not ever. The speed of light is not a speed limit we might one day overcome. It's a property of reality itself. It defines the relationship between space and time, between energy and matter. It is as fundamental to the universe as gravity or the existence of atoms. At this speed, light can circle the entire Earth about 7.5 times in a single second. Think about that. In the time it takes you to say the word now, light has traveled around the planet multiple times. It can travel from New York to Los Angeles and back roughly 37 times before you finish blinking. The fastest commercial airplane flies at about 900 kilometers per hour. Light travels more than 1 million times faster than that. The fastest car ever built, the Thrust SSC, reached about 1,200 kilometers per hour. Light is roughly 900,000 times faster. Even the Parker Solar Probe, the fastest spacecraft humans have ever built, reaches speeds of about 192 kilometers per second at its peak. And even that is only about 0.064% of the speed of light. By any human standard, light is extraordinarily fast, incomprehensibly fast. But space is extraordinarily large, and when you put these two facts together, something interesting and ultimately unsettling happens. Light speed, as fast as it is, becomes almost painfully slow compared to the distances it needs to cover. Let's start close to home and work our way outward. The moon is about 384,000 kilometers from Earth. Light covers that distance in about 1.3 seconds. That means when you look up at the moon on a clear night, you're not seeing the moon as it is right now. You're seeing it as it was 1.3 seconds ago. The moon you observe is always slightly in the past. Now, 1.3 seconds is not much of a delay. You'd never notice it in everyday life. But during the Apollo missions, this delay mattered. When astronauts on the lunar surface spoke to mission control in Houston, there was a lag of about 1.3 seconds each way. Every word the astronauts said took over a second to reach Earth as a radio signal, traveling at the speed of light. Every response from Houston took another 1.3 seconds to reach the moon. This created a round-trip delay of nearly 3 seconds for every exchange. You can actually hear this in the original recordings if you listen carefully. There's always a pause, a gap, a hesitation in every conversation. It wasn't because the astronauts or the engineers were slow to respond. It was because the radio signals, traveling at the fastest speed anything can travel, still needed time to cross the 384,000 kilometers between Earth and the Moon. This is a small delay, barely noticeable in casual listening, but it's real. And it's the first hint of something much larger and much more consequential. Now let's move outward. The Sun is about 150 million kilometers from Earth. Astronomers call this distance 1 astronomical unit, or AU. Light from the Sun takes approximately 8 minutes and 20 seconds to reach us. This means every time you step outside and feel sunlight on your face, that light left the Sun over 8 minutes ago. The sun you see hanging in the sky is not the sun as it exists right now. It's the sun from the past. It's a memory made of photons. If the sun suddenly vanished this very instant, you wouldn't know for over 8 minutes. Earth would continue orbiting a star that no longer existed. Plants would continue photosynthesizing with light from a dead source. You'd keep seeing it, keep feeling its warmth, completely unaware that it was already gone. The light carrying the information about its disappearance would still be racing across 150 million kilometers of empty space at 300,000 kilometers per second. And for 8 minutes and 20 seconds, you'd be living in a universe where the sun still existed as far as you could possibly tell, even though it didn't. This is a strange thing to sit with. We tend to think of seeing as knowing. If you can see something, you know what's happening to it right now. But that assumption only holds true when the distances are small enough for light to cross them, almost instantly. When distances grow large, seeing and knowing become separated. You see the past. You know only what was, not what is. And the farther you look, the deeper into the past you see. Mars, at its closest approach to Earth, sits about 55 million kilometers away. Light takes roughly 3 minutes to cross that gap. At its farthest, when Mars and Earth are on opposite sides of the Sun in their respective orbits, the distance swells to about 400 million kilometers, and the light travel time stretches to over 22 minutes. This delay has real, practical consequences for space exploration that most people never think about. When NASA engineers operate the Perseverance rover on the surface of Mars, every command they send takes between 3 and 22 minutes to arrive, depending on where Mars is in its orbit at that particular time. And every piece of data the rover sends back, every photograph, every sensor reading, every status report, takes the same amount of time to reach Earth. You cannot drive a rover on Mars in real time the way you'd drive a remote-controlled car in your backyard. If the rover encounters an obstacle, if a wheel gets stuck on a rock, or a sensor malfunctions, or the terrain ahead turns out to be impassable, mission control won't even know about it for minutes. Then, they have to analyze the problem, which takes more time. Then, they write new commands, which takes more time. Then, they transmit those commands, which takes more minutes. By the time the solution arrives at Mars, the situation could have changed entirely. A problem that might take 5 seconds to fix with a toy car on your living room floor can take an entire hour or more to address on Mars. This isn't an engineering failure. It's not a limitation of our radio equipment or our software. It's physics. The speed of light is finite and Mars is far away. There's nothing anyone can do about it. Moving further out into the solar system, the delays grow dramatically. Saturn is about 1.2 billion kilometers from Earth at its closest approach. Light takes roughly 1 hour and 20 minutes to make the trip. When the Cassini spacecraft was orbiting Saturn between 2004 and 2017, collecting some of the most spectacular images of the ringed planet ever taken, every photograph it captured took over an hour to reach Earth. Scientists on the ground couldn't watch what Cassini was seeing and react to it. They couldn't steer the spacecraft in real time, adjusting its course as new data came in the way a pilot adjusts a plane. Instead, they had to program entire command sequences days or even weeks in advance, upload those sequences to the spacecraft, and trust that Cassini would execute them correctly and autonomously. If something went wrong, if a thruster misfired, or a sensor gave an unexpected reading, the spacecraft had to handle it on its own. It had to be smart enough to recognize the problem and switch to a safe mode. Because by the time engineers on Earth even learned about the problem and sent corrective commands, over 2 hours would have passed. The situation could have resolved itself, worsened, or changed completely in that time. Now, let's leave the solar system entirely. Voyager 1, launched in 1977, is currently the most distant human-made object in existence. It has been traveling for nearly 50 years, moving at about 17 kilometers per second, which is roughly 61,000 kilometers per hour. That's incredibly fast by any human standard. At that speed, you could cross the entire continental United States in about 2 minutes flat. You could circumnavigate the Earth in roughly 40 minutes. And yet, after almost half a century of continuous travel through the vacuum of space with absolutely nothing to slow it down, no friction, no air resistance, just pure uninterrupted motion, Voyager 1 is only about 24 light hours from Earth. Less than 1 full light day. That means signals from Voyager take nearly a full day to reach us. A command sent to the spacecraft this morning won't arrive until tomorrow morning. And any response from Voyager won't reach us until the morning after that. Every single conversation with humanity's most distant emissary is a 2-day round trip. And in cosmic terms, Voyager is still practically in our front yard. It hasn't even left the sun's broader neighborhood. The nearest star beyond our sun is Proxima Centauri, part of the Alpha Centauri triple star system. It's a small red dwarf, much dimmer and cooler than the sun, orbiting at about 4.24 light years from Earth. 4.24 light years. That means the light you see from Proxima Centauri tonight, if you could see it, because it's too dim for the naked eye, left that star over 4 years ago. You're seeing it as it was more than 4 years in the past. If something dramatic happened to Proxima Centauri right now, if it erupted with a massive stellar flare or somehow dimmed significantly, we wouldn't know for over 4 years. The information would be traveling toward us at the absolute fastest speed the universe permits, and it would still take more than 4 years to arrive. At Voyager 1's current speed, reaching Proxima Centauri would take roughly 73,000 years. 73,000 years, modern humans, Homo sapiens, have only existed for about 300,000 years. You could have launched your mission when the earliest human cave paintings were being created, and it still wouldn't have arrived yet. This is the nearest star, the closest one, our immediate next door neighbor in the galaxy. And it might as well be on the other side of the universe given our current ability to reach it. Sirius, the brightest star in the night sky, is about 8.6 light years away. The light entering your eye when you gaze at Sirius tonight began its journey 8.6 years ago. If you're 25 years old, that light left Sirius when you were about 16, probably in high school. You're seeing a younger version of that star, not the star as it exists in this present moment. Vega, another of the brightest stars, is about 25 light years away. If you're 25, the light you see from Vega tonight left that star the very year you were born. It's been traveling through the cold, empty void of interstellar space for your entire life, crossing roughly 237 trillion kilometers, just to land on your retina this evening. Betelgeuse, the red supergiant marking Orion's shoulder, is roughly 650 to 700 light years away. The light you see from Betelgeuse tonight started its journey around the year 1325. That was during the medieval period. The 100 Years' War between England and France hadn't started yet. The Black Death hadn't swept across Europe. Dante had just finished writing the Divine Comedy. The Renaissance was still more than a century away. Gutenberg's printing press wouldn't be invented for another 100 years after that. And all that time, those photons were traveling in perfect silence, crossing the vast darkness between Betelgeuse and Earth at 300,000 kilometers every single second for 700 years straight, just to reach your eye tonight. You were connected to that star across 7 centuries of travel, linked by photons that have been journeying since before the modern world existed. Here's what makes Betelgeuse particularly interesting. It's a massive star nearing the end of its life. Stars like Betelgeuse burn through their fuel much faster than smaller stars. At some point within the next 100,000 years or so, Betelgeuse will explode as a supernova. When it does, it will briefly shine as bright as the full moon in Earth's sky, visible even during the daytime. It will be one of the most spectacular astronomical events in recorded human history. But here's the unsettling part. It might have already exploded. The explosion could have happened centuries ago. Maybe it blew itself apart in 1500, or 1600, or 1700. We would have absolutely no way of knowing. The light from that explosion would still be traveling toward us, covering 300,000 kilometers every second, racing across 700 light years of empty space. If Betelgeuse exploded in the year 1600, we won't see it until approximately the year 2300. The star could already be gone right now, completely destroyed in a cataclysmic supernova explosion, scattered across space as an expanding cloud of gas and dust. And we'd still see it shining peacefully in Orion's shoulder. For centuries to come, we'd be looking at a ghost, an image of something that no longer exists, and we wouldn't know the difference. This is what it truly means for light to have a finite speed. Every time you look deeper into space, you look further back in time. The two are inseparable. You cannot separate where something is from when you're seeing it. Distance and time become fundamentally linked in a way that our everyday experience doesn't prepare us for. You cannot see a distant object as it is right now. You can only see it as it was when the light left it. And the farther away it is, the older the image you're receiving. Looking out into space is looking back in time. A telescope is a time machine, not in the science fiction sense of physically transporting you to another era, but in the very real sense that it lets you see the universe as it was in the past. The deeper you look, the further back you go. Now, here's where this becomes truly profound. The universe has an age. It is not eternal. It has not existed forever. It began. It had a starting point. The universe is approximately 13.8 billion years old. The Big Bang, the event that initiated everything, occurred 13.8 billion years ago. Before that moment, there was no space, no time, no matter, no energy, at least not in any form we currently understand. Everything that exists, every galaxy, every star, every planet, every atom in your body, every photon of light you've ever seen, all of it traces back to that singular beginning. Because the universe has a finite age, there's a limit to how far light could have traveled since the Big Bang. If the universe is 13.8 billion years old, then light has had at most 13.8 billion years to travel toward us from any direction. This creates a boundary, a sphere centered on our location in space, beyond which light has simply not had time to reach us. Anything beyond that boundary is invisible to us, not because it doesn't exist, Not because we lack the technology to detect it. Not because our telescopes aren't powerful enough or our sensors aren't sensitive enough, but because the light from those regions has not arrived yet. It's still on its way. Or, as we'll explore soon, it may never arrive at all. This boundary is real. It's called the particle horizon, and it represents the absolute outermost limit of our observable universe. Every telescope ever built, from Galileo's first crude spyglass in 1609 to the Hubble Space Telescope orbiting high above Earth's atmosphere to the James Webb Space Telescope, positioned 1.5 million kilometers from Earth at the second Lagrange point. Every single one of these instruments can only detect objects within this boundary. No instrument, no matter how powerful, no matter how technologically advanced, can see beyond it. You could build a telescope the size of the Earth. You could build one the size of Jupiter. You could build one the size of the entire solar system. And it would not matter. The light from beyond the particle horizon hasn't reached us. There is nothing there to detect. No signal to pick up. No photon to capture. The universe itself is the limit, not our engineering, not our ingenuity, not our funding. The cosmos has drawn a line, and we cannot cross it. This creates something remarkable and sobering. What we call the observable universe is not the universe. It's just the part of the universe whose light has had time to reach us since the Big Bang. It's our window, our bubble of visibility. Everything we know about the cosmos, every galaxy we've ever photographed, every distance we've ever measured, every structure we've ever mapped, every cosmological model we've ever built, all of it comes from within this bubble. What lies beyond it is, for now, unknown. And as we will see in the course of tonight's exploration, some of what lies beyond it will remain unknown permanently. Not temporarily unknown, not waiting for better instruments, but permanently, structurally, fundamentally unknowable. Hidden from us not by our limitations, but by the architecture of the universe itself. But here's where things take a strange and unexpected turn. You might reasonably assume that if the universe is 13.8 billion years old, then the observable universe should be 13.8 billion light years in radius. Light has had 13.8 billion years to travel, so it should have covered 13.8 billion light years. That's straightforward arithmetic. But that is not what we observe. The observable universe is not 13.8 billion light years in radius. It's about 46.5 billion light years in radius. That makes it roughly 93 billion light years across from one side to the other. That number should stop you cold. How can the observable universe be larger than the distance light could have traveled in the age of the universe? How can we detect objects that are 46 billion light years away if the universe has only existed for 13.8 billion years? That seems impossible. It seems like it must violate the speed of light. The very law we just spent all this time establishing as absolute and unbreakable, but it doesn't violate it, not even slightly. And the reason it doesn't is one of the most important and counterintuitive facts about the cosmos we inhabit. The universe has been expanding the entire time the light was traveling toward us. Space itself has been stretching. Not the objects within space flying apart through some pre-existing void, but the actual fabric of space growing, expanding, creating more distance between objects that are not held together by gravity or other forces. The light left a distant galaxy billions of years ago when that galaxy was much closer to us than it is now. While the light was in transit, crossing the unimaginable void between that galaxy and our eyes, the space it was traveling through was expanding beneath it. The galaxy that emitted the light was being carried farther and farther away by the stretching of space. By the time that ancient light finally reached our telescopes, the galaxy that originally emitted it was no longer where it had been. It had been carried outward by the expansion. It was now much, much farther away than it was when the light first began its journey. This means the light traveled for 13 billion years, but the galaxy that emitted it is now 46 billion light years away, because space expanded relentlessly during the entire journey. The light crossed a certain physical distance, yes, but the starting point and ending point of that journey both moved during the trip. The universe stretched while the photons were in flight. This is not a trick of numbers or an artifact of how we measure things. It's a real, physical process that's been happening continuously since the Big Bang. And it changes everything about how we understand the size, the shape, and the limits of the observable universe. It means the boundary of what we can see is not simply determined by the age of the universe, it's determined by the age of the universe combined with how much space has expanded during that time. And that expansion, as we're about to discover, is not slowing down, it's speeding up. And that acceleration is what transforms the observable universe from a temporary limitation into a permanent prison. A horizon we can never cross, no matter how long we wait, no matter what we build, no matter how clever we become. So we've arrived at a number that should have disturbed you. The observable universe is about 93 billion light years across, despite the universe being only 13.8 billion years old. That seems like a contradiction. If nothing can travel faster than light, and light has only had 13.8 billion years to travel, how can the universe we observe be so much larger than 13.8 billion light years? The answer lies in one of the most important discoveries in the history of science. The universe is expanding, space itself is growing, and this single fact changes everything about what we can see, what we can know, and what will forever remain hidden from us. Let's go back to where this discovery began, because the story itself is remarkable. For most of human history, people assumed the universe was static. It just existed. It had always been there, unchanging in its overall structure. Stars moved across the sky, planets wandered among the constellations, comets appeared and disappeared, but the universe itself, the stage on which all of this played out, was thought to be fixed, permanent, eternal. Even Einstein, when he first applied his general theory of relativity to the universe as a whole in 1917, assumed the universe was static. His equations actually predicted that the universe should be either expanding or contracting, that a static universe was unstable and should collapse under its own gravity. But Einstein was so convinced the universe had to be static that he added a term to his equations called the cosmological constant, a kind of anti-gravity force designed to hold the universe still and prevent it from collapsing. He later reportedly called this the biggest blunder of his career, because the universe, as it turned out, was not static at all. It was expanding, just as his original equations had predicted. The discovery came from an American astronomer named Edwin Hubble, working at the Mount Wilson Observatory in California. In the 1920s, Hubble was studying what were then called spiral nebulae, faint fuzzy patches of light visible through large telescopes. At the time, There was a fierce debate in astronomy about what these objects were. Some astronomers believed they were clouds of gas within our own Milky Way galaxy. Others believed they were separate galaxies entirely, vast collections of stars far beyond our own. Hubble settled the debate. Using a powerful 100-inch telescope, he identified a special type of variable star called a Cepheid in the Andromeda Nebula. Cepheid variables are stars that pulse in brightness with a period that's directly related to their intrinsic luminosity. By measuring how bright a Cepheid appears from Earth and comparing that to how bright it actually is, you can calculate how far away it is. Hubble's measurements showed that the Andromeda Nebula was far too distant to be inside the Milky Way. It was a separate galaxy, millions of light years away. In a single stroke, the known universe expanded enormously. The Milky Way was not the whole cosmos. It was just one galaxy among many. But Hubble wasn't done. He continued studying galaxies, measuring their distances, and analyzing the light they emitted. And he noticed something extraordinary. The light from nearly every galaxy he studied was redshifted. To understand what this means, you need to know a little bit about how light works. Light is an electromagnetic wave. It has a wavelength. The distance between successive peaks of the wave, different wavelengths, correspond to different colors. Short wavelengths appear blue, long wavelengths appear red. When an object that emits light is moving away from you, the wavelengths of that light get stretched out, shifted toward the red end of the spectrum. This is called redshift, and it's the light equivalent of the Doppler effect you hear when an ambulance siren drops in pitch as it drives away from you. The sound waves get stretched, lowering the frequency. Light waves get stretched too, increasing the wavelength and making the light appear redder. Hubble found that the light from distant galaxies was consistently redshifted. And more importantly, he found a relationship between how far away a galaxy was and how much its light was redshifted. Galaxies that were twice as far away had roughly twice the redshift. Galaxies 3 times farther had 3 times the redshift. This meant that the farther away a galaxy was, the faster it appeared to be moving away from us. This relationship, published in 1929, became known as Hubble's law, and it was one of the most revolutionary discoveries in the history of science, because it meant the universe was expanding. Now, here's where most people get confused, and it's crucial to get this right. When we say the universe is expanding, we don't mean that galaxies are flying apart through space like shrapnel from an explosion. That's a common misconception, and it leads to all kinds of wrong conclusions. What's actually happening is far stranger and far more profound. Space itself is expanding. The fabric of the universe, the actual distance between things, is growing. New space is being created between objects that aren't held together by local forces like gravity or electromagnetic attraction. Think of it this way. Imagine you have a balloon, and you draw dots all over its surface with a marker. Each dot represents a galaxy. Now, imagine you start inflating the balloon. As the balloon expands, every dot moves away from every other dot. Not because the dots are sliding across the surface of the balloon, but because the surface itself is stretching. The dots are staying put on the rubber. They're not moving through the surface, but the distances between them are increasing because there's more surface now, more rubber between each pair of dots. This is what's happening to the universe. Galaxies aren't flying through space. They're sitting relatively still in their own local patches of space, but the space between them is expanding, stretching, creating more distance. And this is happening everywhere, in all directions, all the time. It's not an explosion from a central point. There is no center. Every point in the universe sees every other sufficiently distant point moving away. If you were in the Andromeda Galaxy looking back at the Milky Way, you see us moving away from you. If you were in a galaxy on the other side of the observable universe, you'd see everything around you receding. Every observer, everywhere in the universe, sees the same thing. Distant galaxies moving away, with the most distant ones moving fastest. This is because the expansion is happening to space itself, not to objects within space. Another useful analogy is raisins in bread dough. Imagine you've mixed raisins into a lump of dough and put it in the oven to rise. As the dough expands, every raisin moves away from every other raisin. A raisin that's close to you might move away slowly, because there's only a little bit of dough between you expanding. But a raisin that's far away moves away faster because there's a lot more dough between you, and all of it is expanding simultaneously. The total expansion between you and a distant raisin is the sum of all the little expansions of all the little bits of dough in between. This is exactly how cosmic expansion works. The more space there is between two galaxies, the more total expansion is occurring between them, and the faster they appear to recede from each other. That's Hubble's law in a nutshell. Distance and recession speed are proportional because expansion is happening everywhere at the same rate, and more distance means more total expansion. The rate at which this expansion is happening is described by a number called the Hubble constant. Its current best measured value is about 67 to 73 kilometers per second per megaparsec, depending on the method used to measure it. Different techniques give slightly different results, and this discrepancy, known as the Hubble tension, is one of the biggest unsolved puzzles in cosmology right now. But the approximate range gives us what we need. A megaparsec is a unit of distance equal to about 3.26 million light years. What this number means is that for every megaparsec of distance between two galaxies, the space between them is expanding at 67.4 kilometers per second. So a galaxy that's 1 megaparsec away is receding at about 67 kilometers per second. A galaxy 2 megaparsecs away is receding at about 135 kilometers per second. A galaxy 10 megaparsecs away is receding at about 674 kilometers per second, and so on. The relationship is linear. Double the distance, double the recession speed. Now here's where this leads to something extraordinary and deeply important for understanding why we can never see the whole universe. If the recession speed increases with distance, and it does, then there must be some distance at which the recession speed equals the speed of light. And beyond that distance, the recession speed exceeds the speed of light. Let me say that again because it's crucial. There are galaxies so far away that the space between us and them is expanding faster than 300,000 kilometers per second, faster than the speed of light itself. This might sound like it violates Einstein's theory of relativity. After all, didn't we just establish that nothing can travel faster than light? Yes, we did. And nothing is violating that law. Here's why. The speed limit in relativity applies to objects moving through space. No particle, no spacecraft, no signal can travel through space faster than light. That's an absolute unbreakable rule. But the expansion of space is not movement through space. It's the growth of space itself. The galaxies beyond a certain distance aren't moving through space faster than light. They're essentially stationary in their local patches of space, just as we're essentially stationary in ours. but the space between us is expanding, and that expansion can proceed at any rate. There's no speed limit on how fast space itself can stretch. Einstein's limit applies to motion through space, not to the behavior of space itself. This is a subtle but absolutely critical distinction. It's the distinction that explains why the observable universe is 93 billion light-years across, and it's the distinction that explains why parts of the universe are forever beyond our reach. Let me make this concrete with a thought experiment. Imagine a galaxy that emitted light toward us 12 billion years ago, when the universe was much younger and much smaller. At that time, that galaxy was relatively close. Let's say it was about 3 billion light years away when the light was emitted. The light began traveling toward us at 300,000 kilometers per second, crossing the space between that galaxy and our position. But during the 12 billion years that light was in transit, space was expanding. The galaxy was being carried farther and farther away. The space the light was traveling through was stretching beneath it, like a conveyor belt moving in the opposite direction. The light kept moving forward at the speed of light, but the space it still had to cross kept growing. Eventually, after 12 billion years, that light reached us. We detect it with our telescopes. We see the galaxy as it was 12 billion years ago. But where is that galaxy now? Not 3 billion light years away. Not 12 billion light years away. It's now roughly 30 billion light years away, because space expanded relentlessly during the entire time the light was traveling. The light made the journey because the expansion, while stretching the path, wasn't fast enough along that particular route to prevent the light from eventually arriving. The photons could outrun the expansion for that particular galaxy at that particular distance. But for galaxies that were even farther away, the expansion was too fast. The light they emitted is still trying to reach us, falling further and further behind as space stretches faster than the photons can cross it. That light will never arrive. Those galaxies are beyond our observable universe, not because they're inherently invisible, but because the expansion of space has made it physically impossible for their light to reach us. This expansion has another consequence that's directly visible in the light we receive from distant galaxies. As light travels through expanding space, its wavelength gets stretched along with the space it's moving through. Light that was emitted as visible light, with wavelengths our eyes could see, gets stretched to longer and longer wavelengths as it crosses billions of light years of expanding space. Blue light becomes red. Red light becomes infrared. Infrared becomes microwave. This is cosmological redshift, and it's different from the Doppler redshift caused by objects moving through space. Cosmological redshift is caused by the expansion of space itself, stretching the light waves as they travel. The more distance the light crosses, the more it gets stretched, and the more redshifted it becomes. This brings us to one of the most important observations in all of cosmology. In 1964, two American radio astronomers named Arno Penzias and Robert Wilson were working at Bell Laboratories in New Jersey using a large horn-shaped antenna originally built for satellite communication. They kept detecting a persistent background noise in their instrument, a faint hiss that seemed to come from every direction in the sky equally. They couldn't eliminate it. They checked their equipment for defects. They even cleaned pigeon droppings from the antenna, thinking that might be the source, but the noise persisted. It was the same in every direction, at every time of day, at every time of year. It was constant and uniform. What Penzias and Wilson had accidentally discovered was the cosmic microwave background radiation, often called the CMB. And it turned out to be one of the most important discoveries in the history of science, earning them the Nobel Prize in Physics in 1978. The CMB is the oldest light in the universe. It's the afterglow of the Big Bang itself, still faintly glowing in every direction, filling all of space with a very faint, very cold radiation. To understand what the CMB is and why it matters for our story, we need to go back to the very early universe. In the first few 100,000 years after the Big Bang, the universe was incredibly hot and incredibly dense. It was filled with a plasma, a superheated soup of electrons, protons, and photons all mixed together. In this plasma, photons couldn't travel very far. Every time a photon tried to move in any direction, it would almost immediately collide with a free electron, get absorbed, get re-emitted in a random direction, and then collide with another electron. The universe was opaque. Light couldn't move through it freely. It was like being in a thick, impenetrable fog where you can't see more than a few inches in front of you. The photons were trapped, bouncing around endlessly, unable to escape. But the universe was expanding, and as it expanded, it cooled. About 380,000 years after the Big Bang, the universe had cooled enough for a critical event to occur. Electrons and protons combined for the first time to form neutral hydrogen atoms. This process is called recombination, and it changed everything. Once the electrons were bound up in atoms, they could no longer scatter photons. The fog cleared. The universe became transparent. For the first time, light could travel freely through space without being absorbed or scattered. The photons that had been trapped in the plasma were suddenly released, free to travel in straight lines across the universe. Those photons have been traveling ever since. For 13.8 billion years, they've been crossing the expanding universe, moving at the speed of light, getting stretched by the expansion of space as they go. When they were first released, they were hot. They were visible light, glowing orange-red, like the surface of a cooling ember. But over 13.8 billion years of travel through expanding space, their wavelengths have been stretched by a factor of about 1,100. What was once visible light is now microwave radiation, very faint, very cold, corresponding to a temperature of about 2.725 Kelvin. That's 2.725 degrees above absolute zero, almost nothing. A faint whisper of radiation, barely above the coldest temperature possible in the universe. This is what Penzias and Wilson detected. That persistent hiss coming from every direction. It was the oldest light in existence, released when the universe was only 380,000 years old, stretched by billions of years of cosmic expansion into faint microwaves. The CMB is essentially a photograph of the universe at 380,000 years old. It shows us the universe as it was before any stars had formed, before any galaxies existed, before any of the structures we see today had begun to take shape. It is the earliest image we can ever obtain of the cosmos through light. And here's the critical point for our story tonight. The CMB represents a second wall. The first wall, the particle horizon, is a distance limit imposed by the finite speed of light and the finite age of the universe. The CMB represents a time limit. Before 380,000 years after the Big Bang, the universe was opaque. No light from that era survives in a form we can detect. The photons from that period were absorbed and re-emitted so many times that they carry no coherent information about what was happening. The CMB is a curtain. We can see up to it, but we cannot see beyond it using light. Everything before that moment, the first 380,000 years of the universe's existence, is hidden behind a wall of plasma. We know it happened. We can model it mathematically. We can make predictions about what conditions were like, but we cannot see it directly. The universe was opaque, and no image from that era will ever reach our telescopes. So now we have two walls. The particle horizon, which limits how far we can see in space, and the CMB, which limits how far back we can see in time. Together, these boundaries define the limits of our observable universe. Everything within these limits is accessible to us, at least in principle. Everything beyond them is hidden by either distance or opacity. These are not temporary barriers waiting for better technology to overcome them. They are fundamental features of the universe we inhabit. Now, let's take stock of what we've established so far. We know the universe is expanding. We know that distant galaxies are receding from us because space is stretching between us and them. We know that the most distant objects in the observable universe are now about 46.5 billion light years away, far beyond the distance light could have traveled in the age of the universe, because space expanded while the light was in transit. We know that there are regions beyond the observable universe from which light has not yet reached us. And we know that the expansion of space can carry objects apart faster than light, which means some of those regions may be fundamentally unreachable. But there's a question we haven't asked yet, and it's the most important question of all. Is the expansion of the universe slowing down, staying the same, or speeding up? Because the answer to this question determines whether the situation gets better or worse over time. If the expansion is slowing down, gradually decelerating under the pull of gravity from all the matter in the universe, then light from more distant regions might eventually catch up and reach us. The observable universe would grow over time. We'd see more and more of the cosmos as eons passed. New galaxies would gradually come into view. The horizon would recede. The prison would slowly open. This is what most astronomers expected through most of the 20th century. Gravity should be pulling everything back, slowing the expansion, maybe even eventually reversing it in a big crunch. The expansion should be decelerating. If the expansion is staying the same, proceeding at a constant rate, then the situation would remain roughly stable. Some light from beyond the current horizon might eventually reach us, but very slowly. The observable universe would grow, but only marginally, over cosmically long time scales. We'd gain a little more visibility over billions of years, but not much. This scenario would be neither hopeful nor dire, just steady, unchanging. But if the expansion is speeding up, if something is actively pushing space apart at an accelerating rate, then the situation is catastrophic for anyone hoping to see more of the universe. If the expansion accelerates, then galaxies that are currently at the edge of the observable universe will be carried away faster and faster. Light from regions we can currently see will eventually be unable to keep up with the expansion. Galaxies that are visible today will gradually fade from view as they're carried beyond our reach. The observable universe wouldn't grow. It would shrink. The horizon would close in. The prison wouldn't open. It would tighten. In 1998, two independent teams of astronomers made a discovery that sent shockwaves through the entire scientific community. They were studying a particular type of exploding star called a Type 1a supernova. These supernovae are special. because they all explode with roughly the same intrinsic brightness, which makes them excellent distance markers. By measuring how bright a Type 1 a supernova appears from Earth, and comparing that to how bright it actually is, you can calculate how far away it is with a remarkable precision. Both teams were using this technique to measure the distances to very distant supernovae, hoping to determine whether the expansion of the universe was slowing down, as most expected, and by how much. What they found shocked everyone. The distant supernovae were dimmer than they should have been. Not brighter, which would indicate the expansion was slowing, and the supernovae were closer than expected. Dimmer, which meant the supernovae were farther away than expected, which meant the expansion of the universe wasn't slowing down at all. It was speeding up. The expansion was accelerating. Something was pushing the universe apart, and that something was getting stronger over time. The leaders of these two teams, Saul Perlmutter, Brian Schmidt, and Adam Riess, were awarded the Nobel Prize in Physics in 2011 for this discovery. It remains one of the most important and most unsettling findings in the history of cosmology. Because whatever is causing this acceleration, whatever force or property of space is pushing the universe apart faster and faster, we don't understand it. We've given it a name. We call it dark energy. But that name is essentially a placeholder for our ignorance. We know it exists because we can measure its effects. The acceleration of the expansion is real and has been confirmed by multiple independent observations. But we don't know what dark energy actually is. We don't know why it exists. We don't know if it will continue at its current rate, increase, or eventually fade. It makes up approximately 68% of the total energy content of the universe, making it the dominant component of the cosmos. And we have almost no idea what it is. We know more about what it does than what it is. And what it does is push space apart with increasing ferocity. Dark energy's effects are subtle at small scales. Within our solar system, within our galaxy, even within our local group of galaxies, the gravitational forces binding everything together are strong enough to completely overpower the expansion. The space between Earth and the Moon is not expanding in any measurable way. The space between the Sun and the planets is not expanding. The space between stars within the Milky Way is not expanding. Gravity wins at these scales. But on larger scales, between galaxy clusters separated by hundreds of millions or billions of light years, where gravitational forces are weak and the distances are vast, the expansion dominates, and it's accelerating. Distant galaxies are being carried away from us faster and faster with every passing moment. This acceleration changes the nature of our observable universe fundamentally. It transforms the observable universe from something that might grow over time into something that is actively shrinking. Not shrinking in the sense that galaxies are getting closer, but shrinking in the sense that fewer and fewer regions of the universe will remain visible to us as time goes on. The acceleration means that galaxies currently at the edge of our observable universe are being pushed away faster than their light can travel toward us. Light they emit right now, at this very moment, will never reach us. It will try. It will race toward us at 300,000 kilometers per second. But the space between us and those galaxies will expand faster than the light can cross it. The photons will fall behind, losing ground with every passing second, getting further from us even as they move toward us. Eventually they'll be hopelessly outpaced, carried away by the relentless expansion of space, doomed to travel forever without ever reaching any observer anywhere, This isn't speculation. This isn't a theoretical possibility that might or might not happen depending on future discoveries. This is happening right now. The acceleration of the expansion is a measured fact, confirmed by the supernova observations, by the pattern of fluctuations in the cosmic microwave background, by the distribution of galaxies in the large-scale structure of the universe, by measurements of how galaxy clusters have grown over cosmic time. Multiple independent lines of evidence all point to the same conclusion. The expansion is accelerating, dark energy is real, and its consequences for the long-term future of the observable universe are profound and irreversible. The observable universe, already limited by the speed of light and the age of the cosmos, already bounded by the particle horizon and the opacity of the early universe, is now facing a third and perhaps most devastating limit. Not just a boundary we can't see past today, but a boundary that is actively advancing toward us. A horizon that is shrinking, a wall that is closing in, and everything beyond that wall, everything being carried away by the accelerating expansion, is being lost to us permanently. This brings us to the most unsettling concept in all of cosmology, the cosmological event horizon. This is the boundary beyond which events occurring right now will never be observable to us. Not in a million years, not in a billion years, not in a trillion years, not ever. Light from beyond the event horizon is running toward us as fast as physics allows, but the space it needs to cross is growing faster than it can cover. Those photons are like a swimmer trying to reach shore while the current carries them out to sea faster than they can swim. They'll never make it. They'll swim forever and never arrive, and the information they carry, the story of what's happening in those distant regions of the universe, is lost. Not temporarily, permanently. It's as if those regions of the universe, for all practical purposes, have ceased to exist as far as we are concerned. What makes this even more haunting is that many of the galaxies we can currently see in our deepest telescope images, galaxies whose ancient light has already reached us, are right now beyond the event horizon. Their past light reached us. We have photographs of them. We know they existed billions of years ago, but any light they are emitting right now at this very moment will never reach us. We have their history, but we've lost their future. We received their ancient messages, but we'll never hear from them again. They're still out there, still shining, still full of stars and perhaps planets and perhaps even life, but they're beyond the horizon now, carried away by the expansion of space, gone from our view forever. The universe we can see is not growing. It's being slowly, inexorably emptied. And what that means for the very distant future, what it means for observers living trillions of years from now, is something that should keep any thinking person awake at night. We've established something deeply uncomfortable. The expansion of the universe is accelerating. Dark energy, whatever it is pushing space apart with increasing force. And this acceleration creates a cosmological event horizon, a boundary beyond which events happening right now will never be visible to us. Light emitted today from galaxies beyond that horizon will never reach Earth. Not because the light is too faint, not because we need better telescopes, but because the space between us and those galaxies is growing faster than light can cross it. The photons are racing toward us at the fastest speed physics allows, and they're losing ground. They will travel forever and never arrive. But understanding that this horizon exists is only the beginning. What truly changes your perspective is understanding what this horizon does over time. Because the event horizon isn't static, it isn't a fixed boundary drawn once and left in place. It's dynamic, and its behavior over cosmic time is perhaps the most unsettling prediction in all of modern cosmology. The observable universe, the bubble of space-time from which we can receive information, is shrinking. Not all at once, not dramatically on human timescales, but steadily, relentlessly, over billions and trillions of years, the universe visible to any observer will contain less and less. Galaxies that are visible today will eventually vanish. The evidence for the Big Bang itself will eventually disappear. And future civilizations, if they exist trillions of years from now, will look out at a cosmos that appears fundamentally different from the one we see today. They will construct an entirely different picture of reality. And that picture will be wrong. Let's walk through what happens. Right now, in this current era, the observable universe contains roughly 2 trillion galaxies. We can see them spread across 93 billion light-years of space. We can detect the cosmic microwave background, that faint afterglow of the Big Bang, coming from every direction. We can measure the redshifts of distant galaxies and determine that they're moving away from us. We can calculate the expansion rate, map the large-scale structure of the cosmos, and piece together the history of the universe from its first moments to the present day. We live in a golden age of cosmological observation. The universe is essentially showing us its autobiography, page by page, written in light, but the autobiography is slowly being erased. Let's start with the galaxies themselves. Right now, we can observe galaxies billions of light years away. Some of the most distant galaxies ever detected by the James Webb Space Telescope are so far away that the light we're seeing left them when the universe was only a few 100 million years old. Those galaxies are now, at this moment, tens of billions of light years away, due to the expansion of space. Many of them have already crossed beyond the event horizon. The ancient light they emitted billions of years ago reached us, and we captured it in our telescope images. But any new light those galaxies are emitting right now will never reach us. We've received their last postcards. From this point forward, we'll never hear from them again. They'll continue to exist out there, evolving, forming new stars, perhaps hosting civilizations of their own. But for us, they're already gone. Now, this is currently happening only to the most distant galaxies. Galaxies that are relatively nearby within a few billion light years are still well within our observable universe. Their light continues to reach us. We can still study them, photograph them, measure their properties. The event horizon is far away, and for galaxies that are close enough, the expansion between us and them is not yet fast enough to prevent their light from reaching us. But the acceleration changes this over time. As dark energy continues to push space apart faster and faster, the event horizon creeps closer. Not in absolute terms, because the horizon is defined by the expansion rate, which is increasing. What happens is that galaxies that are currently within the observable universe gradually get carried beyond the horizon as the expansion between us and them accelerates. One by one, galaxy by galaxy, the cosmos empties from the outside in. The most distant galaxies disappear first, then slightly closer ones, then closer ones still. Each one is carried beyond the event horizon by the accelerating expansion of space, and once it crosses that boundary, it's gone forever. This doesn't happen like a light switch being flipped. A galaxy doesn't suddenly blink out of existence from our perspective. What happens is more gradual and in some ways more eerie. As a galaxy approaches the event horizon, the light we receive from it gets more and more redshifted. The expansion stretches the wavelengths of its light further and further toward the red end of the spectrum, then into infrared, then into microwave, then into longer and longer radio waves. The light gets dimmer and dimmer as it's stretched and diluted. The galaxy appears to slow down in time from our perspective, a consequence of the extreme redshift. Events that take 1 year in the galaxy's local time appear to take longer and longer from our point of view. The galaxy seems to freeze, fading in brightness and redshifting into invisibility, approaching the event horizon asymptotically without ever quite appearing to cross it. But for all practical purposes, it becomes undetectable. Its light is stretched to wavelengths so long and energies so low that no conceivable instrument could detect it. The galaxy vanishes from our sky, not with a bang, but with a slow, silent fade into nothingness. This process is happening right now, and it will continue for billions of years, but the real consequences become apparent on much longer timescales. Let's jump forward in time, not by millions of years, not by billions, but by trillions. The Milky Way is part of a small collection of galaxies called the Local Group. This group contains about 50 galaxies, including Andromeda, the Triangulum Galaxy, and dozens of smaller dwarf galaxies. These galaxies are gravitationally bound to each other. The gravitational attraction between them is strong enough to overcome the expansion of space at these relatively small distances. The Local Group will remain intact even as the universe around it expands. In fact, in about 4.5 billion years, the Milky Way and Andromeda will merge into a single large elliptical galaxy that some astronomers have nicknamed Milkdromeda. This merger will combine roughly 1.5 trillion stars into one massive galaxy. The other smaller galaxies in the Local Group will eventually be absorbed as well, consumed by the gravitational pull of this growing combined structure. Over tens of billions of years, the entire Local Group will collapse into a single galaxy, a gravitationally bound island in an increasingly empty ocean of expanding space. And here's the devastating part. Beyond the Local Group, everything else will eventually disappear. Every galaxy cluster, every supercluster, every cosmic filament, every structure that lies beyond the gravitational reach of our Local Group will be carried away by the accelerating expansion. The Virgo cluster, that massive collection of over 1,000 galaxies about 54 million light-years away, will be carried beyond the event horizon. The great cosmic walls and filaments that form the large-scale structure of the universe will be stretched and dispersed. Laniakea, the supercluster of 100,000 galaxies that our Local Group belongs to, will be torn apart as the expansion overcomes the gravitational bonds holding it together. Only the most tightly bound structures, like our Local Group, will survive intact. About 100 billion years from now, give or take, virtually every galaxy outside the Local Group will have been carried beyond the event horizon. Observers in our galaxy, or whatever galaxy exists at that time after the Milky Way and Andromeda have merged, will look out at the sky and see nothing beyond their own galaxy. No other galaxies, no distant clusters, no cosmic web, just their own galaxy hanging alone in an apparently empty universe. The night sky beyond the galaxy's stars will be perfectly black. Not because the universe is empty, not because those other galaxies have been destroyed. They're still out there, still full of stars, still evolving. But the light from all of them will have been stretched beyond detection. redshifted into oblivion, carried away by the expansion of space faster than any photon could ever hope to cross the growing void. But losing the visible galaxies is just the beginning. The cosmic microwave background, that crucial afterglow of the Big Bang that tells us so much about the origin and early history of the universe, will also disappear. The CMB is already very faint, corresponding to a temperature of about 2.725 Kelvin. As the universe continues to expand, the CMB will be stretched to even longer wavelengths and lower energies. Over hundreds of billions of years, it will become so faint, so redshifted, so diluted, that it will be completely undetectable. No instrument, no matter how sensitive, will be able to pick it up above the quantum noise floor of empty space. The whisper from the beginning of time will finally fall silent. And with the CMB gone, so goes the most direct evidence that the Big Bang ever happened. Think about what that means. Right now, the CMB is one of the strongest pieces of evidence for the Big Bang. It was predicted by Big Bang theory before it was observed. It matches the theoretical predictions with extraordinary precision. It shows us what the universe looked like when it was only 380,000 years old. Without it, a crucial pillar of our cosmological understanding vanishes. But that's not the only evidence that will be lost. The redshifts of distant galaxies, the observation that first told us the universe was expanding, will also be gone. If there are no visible galaxies beyond your own, you can't measure their redshifts. You can't deduce that they're moving away. You can't calculate the expansion rate. You can't infer that space is stretching. The very discovery that launched modern cosmology, Hubble's observation that distant galaxies are receding, becomes impossible to replicate because there are no distant galaxies to observe. The primordial abundances of light elements, another key piece of evidence for the Big Bang, will also be harder to interpret. Big Bang nucleosynthesis, which occurred in the first few minutes after the Big Bang, produced hydrogen, helium, and trace amounts of lithium and deuterium in specific ratios that match our observations beautifully. But those ratios also depend on our understanding of the universe's early conditions, which in turn depends on the CMB and the expansion history of the cosmos. Without those other pieces of evidence, the elemental abundances become isolated data points that could potentially be explained by other theories. So imagine a civilization arising in this far future, trillions of years from now. Intelligent beings who develop science, who build telescopes, who look up at their sky and try to understand the universe they live in. What would they see? They would see a single galaxy, their own containing perhaps 1 trillion or so stars. Beyond that galaxy, they would see nothing. Empty, black, featureless space extending in all directions to infinity. No other galaxies, no cosmic microwave background, no evidence of expansion, no evidence of a Big Bang. What cosmology would they develop? They would almost certainly conclude that the universe consists of a single galaxy floating in an infinite, static void. Their universe would look exactly like what astronomers in the early 20th century believed our universe was: a single island of stars in an unchanging sea of emptiness. They would have no reason to think the universe had a beginning, no reason to think it was expanding. No reason to suspect the existence of dark energy or the cosmic microwave background, or the 2 trillion galaxies that once filled the sky. All of that evidence would have been carried away by the expansion of space, erased by the very phenomenon it once helped us discover. This is a deeply sobering thought. These future scientists wouldn't be stupid. They wouldn't be making errors. They'd be applying the scientific method rigorously, drawing conclusions from the best available evidence, just as we do. But the evidence available to them would be fundamentally incomplete. The universe would have hidden its own history. The expansion of space would have erased the clues, carried them beyond the horizon, made them permanently inaccessible. Those future scientists would construct a model of the universe that would be self-consistent, logically coherent, and completely wrong. Not because they failed as scientists, but because the universe denied them the evidence they needed to get the right answer. This raises a haunting question about our own situation. Are we in the same position? Have crucial pieces of evidence already been carried beyond our horizon? Is our picture of the universe incomplete in ways we can't detect because the missing evidence is forever beyond our reach? We have no way to know for certain. We can observe the observable universe and build models that explain what we see. But we cannot verify whether those models accurately describe the universe as a whole, because we can only see a fraction of what exists. And this brings us to an essential distinction that runs through everything we've been discussing tonight. The difference between the observable universe and the total universe. These are not the same thing, and confusing them leads to fundamental misunderstandings about our cosmic situation. The observable universe is a sphere roughly 93 billion light-years across, centered on our location. It contains everything whose light has had time to reach us since the Big Bang. We can study it, map it, photograph it, and build models to describe it. It is the domain of observational cosmology, the region of space-time accessible to our instruments. The total universe is everything that exists. All of space-time, including regions whose light has never reached us and never will. The total universe could be much larger than the observable universe. It could be enormously larger. It could even be infinite. We don't know its size because we can't observe it directly. Everything we know about the total universe is inferred, not measured. It's extrapolation, not observation. And this is a crucial distinction that must be maintained carefully. What do we actually know? We know from observations of the cosmic microwave background that the observable universe is spatially flat to an extraordinary degree of precision. The measurements from the Planck satellite, which studied the CMB in unprecedented detail between 2009 and 2013, show that the geometry of space is flat, meaning that the angles of a triangle add up to 180 degrees and parallel lines never converge or diverge to within a margin of error of about 0.4%. This flatness is consistent with a universe that extends far beyond what we can see. If the universe were finite but only slightly larger than the observable universe, we would likely detect a slight curvature in the CMB. The fact that we don't detect any curvature suggests that the total universe is much, much larger than the observable portion. Some cosmological models based on inflationary theory, the idea that the universe underwent a brief period of exponential expansion in its first fraction of a second, suggests the total universe could be incomprehensibly larger than the observable universe. Some estimates put it at 10 to the power of 23 times larger, or even more. Other models suggest the universe could be spatially infinite, extending forever in all directions with no boundary and no edge. But these are inferences, not observations. They're based on models that fit the data we can see, extrapolated to regions we can't see. The models might be right, they might be wrong. There might be features of the universe beyond our horizon that our models don't account for. that we have no way of knowing about. The total universe might have different properties in different regions. The laws of physics might vary in ways we can't detect because the regions where they vary are forever beyond our observational reach. We simply don't know, and the honest scientific answer is that we may never know. This is profoundly different from most limitations in science. Usually when scientists encounter a boundary to their knowledge, they can at least imagine a way to overcome it. Can't see atoms? Build a more powerful microscope. Can't detect distant galaxies? Build a bigger telescope. Can't measure gravity waves? Build a more sensitive detector. Scientific progress has been driven by the steady expansion of our ability to observe, measure, and test. But the cosmological event horizon is different. It's not a practical limitation, it's a fundamental one. No telescope of any size, no detector of any sensitivity, no technology of any kind can see beyond it. The information is not just hard to access, it's physically, structurally, permanently inaccessible. The expansion of space has placed an absolute limit on what we can know, and that limit cannot be overcome by any means consistent with the laws of physics as we understand them. Now, let's be clear about one thing. When we say the observable universe is shrinking, we mean the region from which new information can reach us is getting smaller over time. The region of space we can currently see, the 93 billion light-year sphere, will technically remain visible in one sense. Light from galaxies we've already received won't unarrive. We've already captured those photons. The Hubble Deep Field images showing galaxies billions of light years away already exist. Those photographs won't vanish, but we won't receive any new light from those same galaxies. We have their past, but not their future. And as the expansion continues to accelerate, the boundary beyond which we can receive new information creeps ever closer, slowly tightening around us like a noose made of expanding space. There's another layer to this that's worth exploring. The expansion doesn't just affect what we can see, it affects what we can reach. Even if we could somehow build spacecraft capable of traveling at close to the speed of light, the accelerating expansion means there are galaxies currently visible in our sky that we could never travel to, even given unlimited time. The space between us and those galaxies is growing too fast. If you launched a spacecraft today aimed at a galaxy that's currently, say, 15 billion light years away, the spacecraft would never arrive. It would travel at nearly the speed of light, but the distance it needs to cover would grow faster than it could close the gap. The destination would recede from the spacecraft like a mirage in a desert, always there, always visible in the telescope, but always unreachable. After billions of years of travel, the spacecraft would actually be farther from the galaxy than when it started, because the expansion of space accumulated faster than the spacecraft could traverse it. This means the universe contains places we can see but never visit. We can photograph them, we can study them, we can analyze the light that reached us from their distant past. But we can never go there, never send a probe there, never establish communication with anyone who might live there. They're visible, but forever out of reach. Right now, the fraction of the observable universe that we could theoretically reach, even traveling at the speed of light for billions of years, is estimated to be roughly only about 3% of the galaxies we can currently see. 97% of the galaxies in the observable universe are already beyond our reach. The expansion has already carried them too far away. We received their light, but that's all we'll ever get. No ship, no signal, no probe will ever bridge the gap. They're in our past, but not in our future. And with each passing moment, that 3% shrinks. More galaxies cross the threshold. More of the visible universe becomes unreachable. The expansion is relentless and it's accelerating. The accessible universe is contracting even as we sit here, and there is nothing anyone can do to stop it. Let's pause here and consider the emotional weight of this. Human beings are explorers. It's one of the defining characteristics of our species. We crossed oceans, mapped continents, climbed mountains, explored the deep sea, sent spacecraft to other planets, and landed on the moon. In every era, when someone pointed to a distant place and said, "We can't go there," someone else eventually found a way. The history of exploration is a history of overcoming limitations, pushing boundaries, reaching the unreachable. But the cosmological event horizon is different. It's not a mountain that's too high or an ocean that's too wide. It's not a technological challenge waiting for a clever solution. It's a property of space-time itself. The expansion of the universe has drawn a line around what we can access, and that line is absolute. No amount of ingenuity, no breakthrough in physics, no leap of technology can push it back. For the first time in human history, we've encountered a limit that is truly, fundamentally, permanently insurmountable. We will never see the whole universe. We will never explore it. We will never know what's beyond the horizon. And the horizon is closing in. This creates a paradox that sits at the heart of modern cosmology. We know the universe is almost certainly larger than what we can observe. The flatness of space-time, the predictions of inflationary theory, the uniformity of the cosmic microwave background, all strongly suggest that the total universe extends far, far beyond our observable bubble. There could be vastly more galaxies, more stars, more planets, more potential for life, more of everything beyond the horizon. But we can never confirm this through direct observation. We can model it, we can calculate probabilities, we can make educated inferences based on the data we have, but we can never look and see. The evidence is forever hidden behind the expanding wall of space. And so we're left with a universe that tantalizes us. It shows us enough to know that there's more. It gives us enough evidence to calculate that the total universe is likely far larger than what we can see. But it refuses to show us the rest. It's like reading the first chapter of a book and being told the remaining chapters exist, but you'll never be allowed to read them. You know the story continues, you just can't see how. What we're confronting here is not a failure of human capability. It's a feature of the universe itself. The cosmos has built walls into its own structure, horizons beyond which information cannot pass, boundaries that separate the knowable from the unknowable. These boundaries are not flaws in our understanding. They are facts about reality. The universe is larger than what it allows us to see. And the gap between what exists and what we can observe is growing every second of every day, widened by the same expansion that reveals the cosmos to us in the first place. We are living in a shrinking bubble of light. Everything we know, everything we've measured, everything we discovered about the cosmos comes from within this bubble. And while the bubble is still enormous, containing trillions of galaxies and stretching across 93 billion light years, it is not the whole story. It's not even close to the whole story. It may be an infinitesimally small fraction of the whole story, and the rest, whatever it contains, however vast and rich and complex it might be, is separated from us by the one barrier that no technology, no discovery, no amount of time can ever overcome: the expansion of space itself. We've arrived at the final stretch of our journey tonight, and it's time to step back and consider the full weight of everything we've discovered. We've learned that light has a finite speed, and that this finite speed means looking into space is looking back in time. We've learned that the universe is expanding, that space itself is stretching, and that this expansion has carried the most distant regions of the cosmos far beyond the distance light could have traveled in the age of the universe. We've learned that the expansion is accelerating, driven by dark energy, and that this acceleration creates a cosmological event horizon, a permanent boundary beyond which events happening right now will never be visible to us. And we've learned that this horizon is shrinking over cosmic time, slowly erasing the evidence of the Big Bang itself and condemning future civilizations to a fundamentally incomplete picture of reality. Now we need to ask the hardest question of all. What does all of this mean? What does it mean for science? What does it mean for the search for life? What does it mean for humanity's future? And what does it mean for us right now, living in this particular sliver of cosmic time? Let's start with what it means for our understanding of the universe. Everything we know about the cosmos, every measurement, every observation, every model, every theory comes from within the observable universe. That's our data set. That's all we have to work with. And we've done extraordinary things with it. We've measured the age of the universe to within about 1% precision. We've mapped the distribution of galaxies across billions of light years. We've detected the cosmic microwave background and used it to determine the geometry of space-time, the density of matter and energy, and the conditions that existed when the universe was only 380,000 years old. We've discovered dark matter and dark energy. We've identified the fundamental forces and particles that govern the behavior of everything we can observe. All of this from within our bubble of visibility. It's one of the greatest achievements of the human mind. But here's the uncomfortable truth that sits underneath all of this achievement. We're extrapolating. When we say the universe is 13.8 billion years old, we mean the observable universe is consistent with being 13.8 billion years old. When we say the universe is spatially flat, we mean the observable universe is spatially flat to the precision of our instruments. When we say the laws of physics are the same everywhere, we mean they appear to be the same everywhere we can observe. We are taking what we can see and assuming it's representative of the whole. And that might be a very good assumption. The cosmological principle, the idea that the universe is roughly the same everywhere on large scales, is supported by everything we've observed. The CMB looks the same in every direction to 1 part in 100,000. The distribution of galaxies appears uniform on the largest scales. There's no evidence of any edge, boundary, or fundamental change in the laws of physics anywhere within the observable universe. All of this supports the idea that the universe beyond our horizon is probably similar to what we see here, but probably is not certainly. And when we're dealing with the total universe, which could be vastly larger than what we can observe, even small differences could have enormous implications. What if the laws of physics change in regions we can't see? What if the density of matter is different beyond the horizon? What if there are structures, forces, or phenomena that exist nowhere within our observable universe but are common elsewhere? We have no way to check. The observable universe might be a representative sample of the total universe, or it might be an atypical pocket with unusual properties. We don't know, and the expansion of space ensures that we may never know. Some cosmological models take this uncertainty seriously. Eternal inflation, for example, proposes that our Big Bang was not a unique event, but rather one instance of a process that happens constantly throughout a much larger multiverse. In this picture, Our observable universe is one bubble in an infinite foam of universes, each potentially having different physical constants, different particles, different laws. The inflationary process that preceded our Big Bang, a brief period of exponential expansion in the first tiny fraction of a second of the universe's existence, might not have ended everywhere simultaneously. In some regions, inflation continued, creating new bubble universes. Those bubble universes are completely disconnected from ours. Light from them will never reach us. Gravity from them will never affect us. They might as well be in a separate reality. We can't observe them, we can't test for their existence, and we can't rule them out. This is important to state clearly. The multiverse is not an observed fact. It's a theoretical prediction that arises naturally from some well-established physics, particularly from inflationary cosmology and certain interpretations of quantum mechanics, but it remains unverified and maybe unverifiable. We cannot see other universes. We cannot detect them. We cannot interact with them. The expansion of space within our own universe already creates a horizon we can never cross. The gap between universes in a multiverse scenario would be even more insurmountable. The multiverse is an idea we can think about, calculate about, and reason about, but it may never be something we can test. And in science, an idea that can never be tested occupies a strange and uncomfortable position, somewhere between hypothesis and philosophy. But even setting aside the multiverse, even focusing only on our single universe, the implications of the cosmological horizon are staggering. The total universe, even if it's governed by the same physics everywhere, could be unimaginably larger than what we can see. If the universe underwent inflation, as most cosmological evidence suggests, then the total universe expanded by a factor so extreme during that brief inflationary period that the numbers become almost absurd. Some inflationary models predict the total universe dwarfs the observable portion by a factor so large that our language barely has words for it. To put that in perspective, if the observable universe were the size of a proton, the total universe in some inflationary models would be larger than the observable universe is right now. That's not a mistake. Listen to that again. If the observable universe were the size of a proton, the total universe in some inflationary models would be larger than the observable universe is right now. The ratio of the total universe to the observable universe might be comparable to the ratio of the observable universe to a single subatomic particle. The observable universe, with its 93 billion light-year diameter and its 2 trillion galaxies and its 200 billion trillion stars, might be an almost infinitesimally small fraction of what actually exists. And we can never see the rest. We can calculate that it's probably there. We can reason about what it might contain, but we can never observe it, photograph it, or send a signal to it. The expansion of space has drawn a permanent curtain around our little patch of reality, and everything beyond that curtain is forever hidden. We touched earlier on the idea that the universe beyond our horizon might contain life we'll never detect, but this deserves deeper examination because the implications are staggering. Are we alone? The search for extraterrestrial life, whether through radio telescopes scanning for artificial signals, space probes analyzing the atmospheres of exoplanets, or rovers drilling into the soil of Mars, is one of the great scientific endeavors of our time. And the answer to this question depends enormously on how much universe there is to search. Within the observable universe, there are roughly 200 billion trillion stars. Many of these stars have planets. Many of those planets are inhabitable zones where liquid water could exist on the surface. Even if the probability of life arising on any given habitable planet is vanishingly small, the sheer number of opportunities might make life common across the cosmos. This is the reasoning behind the Drake equation and the optimism of many astrobiologists. But here's what the cosmological horizon adds to this picture. Those 200 billion trillion stars are only what's in the observable universe. If the total universe is vastly larger, and most models suggest it is, then the total number of stars might be incomprehensibly higher. There could be civilizations beyond our horizon, perhaps billions of them, living on planets orbiting stars in galaxies we will never see. They might be older than us, more technologically advanced than us, building structures and creating art and asking the same questions about whether they're alone. And we will never know they exist. They will never know we exist. The expansion of space has separated us permanently, not by the distance between our galaxies, which is already immense, but by the fundamental inability of light or any signal to cross the expanding void between us. This adds a new dimension to the Fermi paradox, the famous question of why we haven't detected signs of alien civilizations, despite the vast number of stars and planets in the universe. The standard Fermi paradox considers only the observable universe, and even within that framework, the distances between stars are enormous enough to make contact extremely difficult. But the cosmological horizon makes the situation far more extreme. The universe might be teeming with life, filled with civilizations that have existed for billions of years, and we would never know. Not because we lack the technology to detect them, not because they're hiding, not because interstellar distances are too great to bridge, though they might be, but because the expansion of space has placed them permanently beyond our reach. The universe could be full and still appear empty to us, because the fullness exists beyond our horizon. This possibility raises a question that borders on the philosophical. If something exists but can never be observed, never detected, never interacted with in any way, does it matter? In one sense, no. If civilizations beyond the horizon have no effect on us and we have no effect on them, their existence is practically irrelevant to our lives. Whether the universe beyond the horizon contains trillions of civilizations or is completely empty changes nothing about our daily experience, our science, our technology, or our future within the observable universe. But in another sense, it matters enormously, because it changes the meaning of our existence. If we're alone in the observable universe, but the total universe is filled with life, then our isolation is an accident of cosmic geography, not a statement about the rarity of life. If the total universe is empty and we truly are the only conscious beings anywhere, that carries a completely different weight. The answer to whether we're alone depends on a question we may never be able to answer, because the evidence is hidden behind a horizon we can never cross. Let's turn now to a more personal question. What does this mean for us? For you specifically, living on this planet, in this era, looking up at the sky tonight. It means something that's both humbling and extraordinary. You are living in a privileged window of cosmic time. Right now, in this era, the universe is showing us its history. The cosmic microwave background is detectable. Distant galaxies are visible. The expansion of the universe is measurable. The evidence for the Big Bang is spread across the sky in every direction, waiting to be read by anyone with the right instruments and the curiosity to look. This will not always be the case. As we've already seen, trillions of years from now, the evidence surrounding us will have been carried away by expansion. The CMB will have faded. The distant galaxies will have vanished. The cosmic story will have been erased. But right now, in this era, the book is still open. We are living in the cosmic equivalent of a clear morning, when the landscape is visible in all directions and you can see for miles. Trillions of years from now, the fog will have rolled in, and the landscape will be hidden. We're the ones who get to see it. We're the generation that has access to the full picture, or at least as full a picture as the universe will ever reveal. The fact that you exist now, in this brief window when the cosmos is still showing its hand, is extraordinary. You are part of a civilization that has decoded the cosmic microwave background, measured the expansion of the universe, detected galaxies 13 billion light years away, and pieced together the history of the cosmos from the Big Bang to the present day. No future civilization will have access to the same evidence. They'll be brilliant, perhaps far more brilliant than us, but they'll be working with incomplete data. We have the full data set, or at least the fullest data set the universe will ever provide. This should change how we think about the knowledge we've gained. Cosmological knowledge isn't just interesting, it's time sensitive. It has an expiration date. The evidence we're using to understand the universe is slowly being carried away by the expansion of space. Measurements that are possible today will not be possible in the deep future. Observations we take for granted, like seeing other galaxies in the sky, will become impossible. The window is open now, and it's closing. Not quickly enough for us to notice in a human lifetime or even in millions of years, but it's closing. And the knowledge we gain while the window is open may be the only knowledge anyone in our corner of the cosmos will ever have about the true nature of the universe. There's something poetic about this, even melancholy. We're like someone standing on a hilltop watching a sunset, knowing that once the light fades, it won't come back. The universe is letting us see something beautiful and profound, something that reveals its deepest nature. And then, it's going to take it away. Not out of cruelty. The universe doesn't have intentions, but out of the simple physics of expansion. Space stretches, light redshifts, horizons close in, evidence fades, and what's left is silence. But let's not end on despair, because there's another way to see all of this. Yes, the universe is larger than what we can observe. Yes, vast regions of space-time are permanently hidden from us. Yes, the observable universe is shrinking over cosmic time, and future civilizations will lack the evidence we currently possess. These are facts, and they're sobering. But they don't diminish what we've accomplished. They amplify it. Think about what we've done. We're a species that evolved on one small planet, orbiting one ordinary star in one galaxy among trillions. We evolved to survive on the African savanna, to find food, avoid predators, and navigate social relationships. Our brains were shaped by natural selection to handle problems on the scale of meters, kilograms, and years. Nothing in our evolutionary history prepared us to think about billions of light years, trillions of galaxies, or the expansion of space-time. And yet, here we are. We figured it out. We discovered that the universe is expanding. We measured the cosmic microwave background. We calculated the age of the cosmos. We mapped structures billions of light years across. We discovered dark energy. We identified the existence of horizons that we can never cross. All of this from one small planet, using instruments we built with our own hands and theories we developed with our own minds. The observable universe might be a tiny fraction of the total universe. We might be seeing only a sliver of what exists. But we saw it. We understood it. We grasped, at least in outline, the shape of the cosmos we inhabit and the limits of what we can know. That's not a failure. That's a triumph. We measured the prison. We mapped the walls. We understood why the walls exist and how they work. And in doing so, we achieved something that the universe itself, vast and impersonal as it is, could never have done on its own. We became conscious of it. We became the universe's way of knowing itself, even if only within the boundaries of what it allows us to see. And here's one final thought that I want to leave you with, because it captures everything we've discussed tonight. The universe is not hiding from us out of malice. It's not testing us. It's not denying us knowledge as some cosmic lesson. The horizons that surround us are simply consequences of the physical laws that govern everything. Light has a finite speed. The universe has a finite age. Space is expanding, and that expansion is accelerating. These are facts, neutral and indifferent, with no agenda and no purpose. They simply are. And because they are, there are limits to what any observer, anywhere in the universe can see. But within those limits, within the bubble of space-time accessible to us, the universe has been astonishingly generous. It has given us a cosmic microwave background that encodes the conditions of the early universe. It has given us billions of visible galaxies whose redshifts reveal the expansion of space. It has given us supernovae that betray the acceleration of that expansion. It has given us a cosmic web of filaments and voids that traces the growth of structure from quantum fluctuations to galaxy clusters. It has given us enough information to reconstruct the history of the cosmos from its first fraction of a second to the present day. We can't see everything, but we can see so much. And what we see is magnificent. The next time you look up at the night sky on a clear, dark night, you will see stars. Thousands of them, scattered across the blackness. Every one of them is part of the Milky Way, your home galaxy. Beyond them, if you have sharp eyes and dark skies, you might see the faint smudge of the Andromeda galaxy, the most distant object visible to the naked eye, sitting about 2.5 million light years away. The light entering your eye from Andromeda began its journey when our ancestors were just beginning to use stone tools. That light has been traveling through expanding space for 2.5 million years to reach you tonight. And beyond Andromeda, invisible to your naked eye but visible through telescopes, there are billions more galaxies. Spirals and ellipticals and irregulars, each containing billions or trillions of stars, each hosting countless worlds, stretching across billions of light years of space. You can't see them without technology, but they're there. And the light from the most distant of them has been traveling since the universe was young, since before the sun existed, since before the atoms in your body had been forged in the cores of ancient stars. You are seeing across time when you look at the night sky. You are seeing the universe's past written in photons, and you are seeing it in a window of cosmic time that will not remain open forever. The evidence that surrounds us, the galaxies and the microwave background and the redshifts and the expansion, all of it is temporary. It will fade. It will be carried away. The universe will eventually hide its own story behind a wall of expanding space. But right now, in this brief, extraordinary moment in cosmic history, the story is visible. The book is open. The evidence is spread across the sky in every direction, and you are here to see it. You, part of a species that has read the cosmic story, not all of it, perhaps not even most of it, but enough to understand its shape. enough to know that the universe began, enough to know that space is expanding, enough to know that there are horizons we can never cross and truths we can never access, and enough to appreciate just how remarkable it is that we've learned this much from one small planet orbiting one ordinary star. We will never see the whole universe. That's the truth we've explored tonight. The speed of light, the expansion of space, and the acceleration of that expansion together create boundaries that are permanent and impassable. Beyond those boundaries, space-time continues. Galaxies shine, stars burn, planets orbit, perhaps life exists and civilizations flourish, but we will never know. We'll never see them, never detect them, never receive a single photon from their skies. They exist beyond our horizon, forever hidden, forever unreachable. And yet, within our horizon, the universe has revealed itself to us with breathtaking generosity. It has shown us enough to understand our place in the cosmos, our moment in cosmic time, and the limits of what we can ever know. We are small. We are brief. We are confined to a bubble of visibility in a universe that is almost certainly far, far larger than anything we can observe. But we are also aware. We are conscious. We understand, at least in outline, the cosmos that created us. And we live in the one window of time when the evidence is still visible, when the story can still be read, when the universe is still showing its hand. That makes this moment precious. Not just your moment on this planet, not just this era in human history, but this cosmological epoch. This brief stretch of cosmic time when the universe is still transparent enough for its secrets to be seen. One day, trillions of years from now, the sky will go dark. The galaxies will have vanished. The microwave background will have faded. The evidence will be gone. And any beings living in that distant future will never know what we knew. But we know. Right now, tonight, we know. We've seen the evidence. We've read the story. We've looked out at the cosmos and understood, at least in part, what we were seeing. And that understanding, fragile and temporary as it may be, is one of the most extraordinary things the universe has ever produced. A collection of atoms on a small planet, looking out at the stars and comprehending the cosmos that made them. That's what we are. That's what you are. And the universe, vast and indifferent as it is richer for it. So tonight, when you look up at the sky, remember this. You are seeing the universe in its prime. You are witnessing the cosmos while the evidence is still there. You are living in the golden age of cosmological knowledge, a window that opened billions of years ago and will slowly close over the trillions of years to come. The universe will never show more of itself than it's showing right now. This is it. This is the view, and you're here to see it. That's something worth appreciating, something worth holding on to, something worth marveling at, even as you go about your ordinary life on this ordinary planet, orbiting this ordinary star. Because the view from here, right now, in this moment, is the best view anyone will ever have, and it's yours. Thank you for joining me tonight on this journey through the limits of what we can see and know about the universe. If this exploration meant something to you, a like or subscribe genuinely helps this channel continue making these deep dives into the cosmos. The universe is vast. Our view of it is limited, but what we can see from here is magnificent. Sleep well tonight under the stars. They're showing you the universe while it's still willing to be seen, and that is a gift beyond measure. Good night.